Welcome to the beautiful world of math. With math, you can take on wings and build whatever your mind conceives. From making a model car to a real car. From your first dollhouse to a real house. Math is a very important tool in today's society, in yesterday's society, in the society to come. Math, math, math. What a powerful tool.
Count with me from 1 to 10. Each number has the same number of boys or girls beside it. Count them if you have to, okay? Are you ready? Let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sequential numbers. Sequential numbers is putting numbers in the correct place. Now that you know how to count 1 to 10, let's see if you can fill in the missing numbers. I know you can do it. Okay, here we go. 1 and 3. What number goes in between 1 and 3? 2. 1, 2, 3. 4 and 6. What number goes in between 4 and 6? 5. 4, 5, 6. 9. What two numbers go before 9? 7, 8. 7, 8, 9. Great job! Now we're going to count 1 to 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
Now we're going to count from 1 to 100. Okay, let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70. 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, and 100. Great job! Now we're going to learn odd and even numbers. Look at the number of girls and boys beside each number if you have to. The odd numbers. 1, 3, 5, 7, 9. Great job. The even numbers. 2, 4, 6, 8, 10. Great job. Now we're going to count by fives all the way to 100. But before we do that, I want to share something with you. Do you know that numbers have a natural rhythm? If you listen very closely, you will hear it as we count by fives all the way to 100. Okay, are you ready? Are you sure? Okay, let's do it. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, and 100. Did you hear the rhythm? That's great. You did very well. That is great. I mean great. Now we're going to count by tens all the way to 100. Are you ready? Let's go. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Faster. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Even faster. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Great job. Now we're going to learn how to count money. But before we do, we have to know how much each coin is worth. First, you have your penny. A penny is worth 1 cent. Then you have your nickel. A nickel is worth 5 cents. And we can't forget that dime. No, we can't forget the dime. The dime is worth 10 pennies, or we'll say 10 cents. And that big quarter, the big shiny quarter, is worth 25 pennies or 25 cents. Now we're going to learn how to count money. Use all of your skills that you learned. Counting by ones, counting by fives, counting by tens, because guess what? You're going to have to use all of those to count money. Okay, here we go. 10 pennies is equal to how many cents? 10 cents. 11 pennies is equal to how many cents? 11 cents. 6 pennies is equal to how many cents? 6 cents. 5 pennies is equal to how many cents? 5 cents. Or we will call it a nickel. 1 nickel is equal to how many cents? 5 cents. Great job. 2 nickels is equal to how much? 10 cents. 3 nickels is equal to how much? 15 cents. 2 nickels and 6 pennies is equal to how much? 16 cents. Great job. I thought I would fool you, but I didn't. You're on top of it. Three nickels and 4 pennies is equal to how much? 19 cents. Great job. 4 nickels is how much? 20 cents. 5 nickels is equal to how much? 25 cents. Great job. 5 nickels and 3 pennies is how much? 28 cents. 6 nickels and 2 pennies is how much? 32 cents. Great job. 8 nickels is equal to how much? 40 cents. 5 dimes is how much? 50 cents. Great job. Because you have what? How many dimes? 5. And 5 dimes is equal to 50 cents. Because guess what? 5 times 10 is 50. That's your multiplication tables. We'll get to those a little later, but it's 50 cents. 1 dime is equal to how much? 10 cents. 1 quarter is equal to how much? 25 cents. Great job. 2 quarters is equal to how much? 50 cents. 3 quarters is equal to how much? 75 cents. 4 quarters is equal to how much? $1. I knew I wasn't going to fool you on that one. $1. That's great. 3 quarters, 1 dime, 1 nickel, and 4 pennies is how much? 94 cents. Great job. 100 pennies is how much? $1. Great job.
Now we will be learning about basic shapes. What shape do you see here? Circle. What shape do you see now? Oval. What shape is this? Rectangle. What shape is this? Square. Great job. Now the last shape is what? A triangle. Now we'll be learning how to tell time. Time is something that's very important in everyday life. First, we will learn how to tell time by the hour. What time do you see below? 4 o'clock. 7 o'clock. 8 o'clock. 5 o'clock. And 3 o'clock. Those are the time by the hour. Now we will be learning time by the quarter hour. What time do you see here? 11:45. Next, 8:45. 2:45. 8:45. Last but not least, 12:45. Half hour. What time do you see here? 3:30. 9:30. And 5:30. Quarter past. What time do you see here? 6:15. 1:15. And 10:15. And last but not least, 4:15. Now we will be learning how to add. Addition. 5 plus 7 equals 12. 9 plus 4 equals 13. 3 plus 8 equals 11. 4 plus 10 equals 14. Great job. 12 plus 5 equals 17. 9 plus 9 equals 18. 6 plus 3 equals 9. Great job.
Subtraction. 9 minus 4 is 5. 14 minus 5 is 9. 21 minus 3 is 18. 13 minus 1 is 12. Great job. 8 minus 3 is 5. Great job. Multiplication. 7 times 4 is 28. 8 times 7 is 56. 4 times 3 is 12. 9 times 4 is 36. 6 times 7 is 42. Great job. Division. 8 divided by 8 is 1. 16 divided by 8 is 2. 24 divided by 8 is 3. 12 divided by 4 is 3. 16 divided by 4 is 4. 20 divided by 4 is 5. 24 divided by 4 is 6. 28 divided by 4 is 7. Great job. Decimals. What are decimals? A decimal is a part. A decimal can be a fraction. A decimal can be called a portion. A decimal can be called a percent. Now they all have different names, but you have to keep in mind they mean the same thing. And by that I mean a decimal is nothing but a part of a whole. For instance, if you have a whole pie and you cut that pie down the middle, then you have 1/2. That 1/2 is a fraction. But guess what? That 1/2 is also a decimal. That 1/2 is also a percent. 1/2 can also be called 50%. 50% can be also called 1/2. 1/2 is a fraction. A decimal. What is a decimal? A decimal is a fraction. A decimal is a percent. A decimal is a fraction. A decimal is a piece. It means a part of a whole. In the chart on the screen, you will see a red decimal. Now, on the left side of that decimal, you have your wholes. On the right side of that decimal, you have your parts. To the left, you will see the red 6, the left of the decimal. That 6 is in the ones place. The 2 is in the tens place. The 3 is in the hundreds place. And that red thousands, 4 places over from the decimal, that's the thousands. 5 places over from that decimal to the left is the 10,000s. 6 places from the left of the decimal is the 100,000s. And 7 places is the millions. To the right of that decimal, that red 7, you have the tens. That 2 is in the hundreds. Then 3 places to the right, you have your thousands. 4 places, you have your 10,000s. 5 places, you have your 100,000s. And 6 places, you have your millions. Great job. $0.50 is equal to $1/2 is equal to 50 cents. A quarter is equal to $1/4 is equal to 25 cents. 1/100, or if it's written out, 1/100th of a dollar. 85 cents is equal to 85 hundredths of a dollar. $7.45 is equal to 7.45, or $7.45. And that decimal, the 7 on the left hand side of that decimal is 7 whole dollars. And that 45 on the right hand side of that decimal is basically telling you that's 45 pennies. So in other words, you have $7.45, or you can say $7.45. You see, decimal has a relevance to fractions, and fractions have a relevance to decimals, and decimals have a relevance to percents. It all means the same thing: wholes and parts. Percents. Percent means out of 100. If you look at the chart on the screen, you'll see that it's broken down into 100 parts. That chart, like we talked about earlier, is broken down to 100 parts, but that chart could just as easily be a dollar bill that's broken down into 100 pennies. Isn't that amazing? We use the percent symbol as a way to write a fraction with a common denominator of 100. Instead of saying 9 out of every 100 artists like to paint with oil, we could say 9% of artists like to paint with oil. A percent can be written as a decimal, and a decimal can be written as a percent by moving the decimal point 2 places to the right like this. A decimal can be written as a percent by moving the decimal point 2 places to the left like this. Isn't that amazing? Remember, percent means out of 100. Here are some practice problems of percent to decimal and decimal to percent. Change to percent, or we're going to change it to a decimal. The first one is 16%. Remember, if you already have percent and you have to change it to a decimal, you move your decimal places 2 places to the left, which will give you 0.16. We're going to go to the immediate right. 0.79 or 79 hundredths. If we're going to change that from a decimal to a percent, we move that decimal places 2 places to the right, which will give you 79%. 0.84, going back to the left. 0.84. If we're going to change 0.84 or 84 hundredths to a percent, we move that decimal places 2 places to the right. 77%. We're going to change that to a decimal, which means we're going to move that decimal 2 places to the left. The next one is 43%. We're going to change that to a decimal, so we'll move that decimal place 2 places to the left, which will give us 0.43 or 43 hundredths. 0.47 or 47 hundredths. We're going to change that 47 hundredths to a percent. We'll move that 2 places to the right, which will give us 47%. 21%. We're going to change that to a decimal. Therefore, we move that decimal place 2 places to the left, which will give us 0.21 or 21 hundredths. And finally, 0.98 or 98 hundredths. We're going to change that to a percent, which means we're going to move that decimal place 2 places to the right, which will give us 98%, which means we have done a great job. Fractions. A fraction is a part of a whole. All the names below mean the same thing: a part, a decimal, a percent, a portion, or a piece. By having a good understanding of all these terms that mean the same thing, you can never be, as you say, tricked, or those are trick questions. There's no such thing as a trick question. Once you know terminology, a part, decimal, percent, portion, piece, all of those words mean the same thing. So nobody can trick you. You can't trick yourself. Once you know terminology and know that all these words mean the same thing, and whenever you see them on a word problem, or you see them on a test, or you see it on your homework, you will know that all of these mean the same thing. So you know you're dealing with part of a whole. So never be deceived or never deceive yourself by this terminology from this day on. Terms of the fraction. Every fraction has a numerator and a denominator. In this fraction, 1/2, 1 is what you call a numerator, and 2 is what you call a denominator. In the fraction 3/4, 3 is your numerator and 4 is your denominator. In the fraction 2/3, 2 is your numerator, 3 is your denominator. 5/6, 5 is your numerator and 6 is your denominator. Here is 1 pie. If we split the pie down the middle and there's 2 people in the room, then we have broken the pie down into 2 pieces and each person will get a piece of the pie. Here is 50% of the pie, or 0.5 of the whole pie. 50%, 0.50, or 1/2 of the pie. All of those are considered fractions, decimals, or percents, and each person will get 1/2 of the pie. If we have 3 people in the room and we split the pie into 3 parts, then we have broken the pie down into thirds, and each person will get 1/3 of the whole pie. Here we have a whole pie. If we break the pie down into 4 parts, because there are 4 people in the room, then we have broken the pie down into fourths, or 25%, or 0.25, or 25%. Here is a whole pie. If there's 8 people in the room and one person takes a piece of the pie, then he has taken 1/8 of the pie. Isn't that amazing? There are 6 cars. 4 of the cars are red and 2 of the cars are blue. 4/6 of the cars are red. 2/6 of the cars are blue. Types of fractions. Proper fraction. A fraction is a proper fraction when the numerator is less than the denominator. 5/6, 3/4, 2/3. In all of these, the numerator is less than the denominator. Improper fractions. A fraction is an improper fraction when the numerator is more than the denominator. 6/5, 4/3, 3/2. Mixed fractions. A fraction is a mixed fraction when you have a whole number and a fraction. 2 and 5/6, 1 and 3/4, 5 and 2/3. We can convert a mixed number to an improper fraction. First, we multiply the whole number by the denominator of the fraction. Then add the numerator of the fraction to the product. For instance, 2 and 5/6. Now follow the arrow. 2 times 6 is 12, plus 5 is 17. We multiply the 6 denominator times 2 the whole number plus 5 the numerator. That's what gives us our 17. Again, 2 and 5/6 mixed number. We multiply 2 times 6, which is the whole number times the denominator, or the denominator times the whole number, and then we add the 5, which gives us 17/6. The next problem below that, 1 and 3/4. We multiply 1 times 4, which is that whole number times that denominator, which gives us 1 times 4 is 4, plus 3, which gives us 7. And we bring our denominator over, which makes that answer 7/4. Again, you multiply your whole number, which is the 1, times the 4 denominator. 1 times 4 gives you 4, plus 3, the numerator. 1 times 4 is 4, plus 3 is 7. You bring your 7 over. Now you have 7/4. 5 and 2/3. 5 times 3 is 15. That 5, your whole number, times the 3, your denominator. 5 times 3 is 15, plus 2 is 17. Bring your 17 over, and bring your 3 over, your denominator. 17 thirds. That's how you do those problems. Great job. Equivalent fractions. Equivalent fractions are fractions that represent the same number. To find out if two fractions are equivalent, divide the denominator into the numerator. For instance, 1/2. You divide 2 into 1.00. 2 goes into 1.00 0.50 times. 0.50, remember, if you translate 0.50 into a percent, it translates into 50%. If you translate 0.50 into a fraction, it translates to 1/2. 2/4. 4 goes into 2.0 0.50 times. That translates to 0.50 to 50% to 2/4, and you reduce 2/4 down, it reduces to 1/2. 4/8. 8 divides into 4.0 0.50 times. 0.50 translates to 50% or 1/2. If you reduce 4/8 down, it translates to 1/2, which is 0.50. All of these fractions translate to 0.50. Now, they're different fractions. They look different to you, so don't be deceived by that. You still go by the same basic concept of dividing your denominator into your numerator, and you're going to come out with 0.50. And when you do that, and you come up with that result, you have equivalent fractions. Great job. Like fractions. Like fractions are fractions that have the same denominator. 1/4, 2/4, 3/4. You can add and subtract like fractions easily. Add or subtract the numerators and write the sum over the common denominator. In this fraction, 1/5 plus 3/5 equals 4/5. In this next fraction, 6/7 minus 2/7 equals 4/7. Like fractions. Here's some more sample problems of addition and subtraction problems that have like fractions. Starting off to the left, 2/5 plus 4/5 is equal to 6/5, which is an improper fraction. We can't leave that answer as an improper fraction. Therefore, we must divide the denominator into the numerator. The denominator is 5 and the numerator is 6. So we divide 5 into 6. 5 into 6 gives us 1. And we read our answer clockwise, starting off at the top. 1 and 1/5. We read the answer again, reading clockwise, and just follow the red arrows. 1 at the top and 1/5. That's how we translate from an improper fraction to a mixed fraction. We divide the 5 into the 6. The next problem is 9/7 minus 3/7 is equal to 6/7. The problem below that is 8/12 minus 5/12 equals 3/12. But 3/12 is not reduced to the lowest terms, because 3 can go into 3 one time and 3 can go into 12 4 times. So 3/12 can be reduced to 1/4. In the next problem, 1/5 plus 2/5 equals 3/5. The problem to the immediate right of that, 3/5 plus 2/5 gives us 5/5. Now remember this, you have to be very careful with this type of problem. Whenever you have a numerator and a denominator the same, you have to divide the denominator into the numerator. In this case, you have 5/5, which will give you the answer 1. 5/5 will give you the answer 1. That is your answer. Now we'll come down to the bottom left of the page. 6/7 minus 3/7 gives us 3/7. And in the last problem, 15/16 minus 7/16 will give us 8/16. But 8/16 is not reduced to the lowest terms because 8 can go into 8 one time and 8 can go into 16 two times. Now, you strike out the 8, 8 going to 8 one time, which will give you that 1 up there as your numerator, and 8 going to 16 two times. You strike out the 16 and 8 going to 16 two times. That's what gives you your answer, 1/2. 1/2 is your answer. Great job. Reducing a fraction to its lowest terms. A fraction is reduced to its lowest terms when its numerator and denominator have no common factors. Unlike fractions. Unlike fractions are fractions that have different denominators. 7/8, 3/6, 4/7. All of these fractions have different denominators. Multiplying fractions. Here we have 2/3 times 1/3. 2 times 1 is 2. And in this case, we're multiplying the numerators because 2 times 1 is 2. And 3 times 3 is 9. So in other words, to solve this problem, we say 2 times 1 is 2. And 3 times 3 is 9. We multiply the numerators to get the numerator in our answer. And we multiply the denominators to get the denominator in our answer. Therefore, our answer is 2/9. Great job. Here are some more sample problems. 4/5 times 1/5 give us 4/25. To the immediate right of that problem, we have 3/5 times 2/3 gives us 5/6. Back over to the left and down. 5/6 times 5/6 gives us 25/36. 1/4 times 3/5 gives us 3/20. Now in this problem, we have a 15 on the left and a 30 on the bottom right. And we have a 6 on the top right as a numerator and an 18 on the bottom left as a denominator. Now, let's look at these problems because we're going to go over a method that's called the cancellation method. We look at the 15 and we look at the 30. The 15 and the 30. Now, what's the highest number that can go into 15 and 30? 15. Great job. 15 goes into 15 one time. That's why we cancel out. That's why this is called the cancellation method. The 15 go into 15 one time. Now we go down to that 30. 15 goes into 30 two times. We cancel out, we slash out the 30 and we put the 2 below that. Then we ask ourselves, what number goes into 6 and 18, the highest number? You got to say the highest number. If you say the highest number, then you won't have to reduce so much at the end. You might not even have to reduce. So you always want to ask yourself, what's the highest number that can go into 6 and 18? That's the way you have to phrase that thing. What number goes into 6 and 18, the highest number? The highest number that'll go into 6 and 18 is 6. 6 go into 6 one time. You run a slash through the 6, they'll give you a 1. 6 goes into 18 3 times. Now, all you do now is multiply your numerators and multiply your denominators, just like you did in the earlier problems. 1 times 1 is 1, and 3 times 2 is 6. Your answer is 1/6. Great job. Multiplying mixed fractions. In this problem, we have 3 and 5/6 times 1 and 1/5. Now, since we're going to multiply mixed fractions, the first thing we have to do is change these into improper fractions. The way that we do that is, look at this problem closely. The first thing we do is multiply 6 times 3, which gives us 18. Look at your arrow and your 1. The first thing is 6 times 3. It gives us 18. Then we say 18 plus 5. The 5 is the numerator. 18 plus 5 gives us 23. Now we have 23/6. That take care of the 3 and 5/6. Now we have to do the same thing to the 1 and 1/5. The first thing we do is multiply that 5 times that 1. 5 times 1 gives us 5. Step number 2. Add the 1 numerator. 5 times 1 is 5, plus 1 is 6. That gives us 6/5. From this point, we have 23/6 times 6/5. Now, we look at the 23 and the 5. The 23 on the left numerator and the 5 denominator. Is there a number that can go into 23 and 5? What's the highest number? There's not a number. So we can't do anything with that. Is there a number that can go into both 6 and 6? Yes. 6 going to 6 one time. 6 going to the other 6 one time. 23 times 1 gives us 23. And 1 times 5 gives us 5. Our answer so far is 23/5. But remember, we can't leave our answer as an improper fraction. Therefore, we have to divide the denominator into the numerator, which means we divide 5 into 23. 5 goes into 23. The closest number we can get and the highest number is 4. 5 times 4 is 20. 23 minus 20 is 3. And we read our answer again clockwise, starting up at top. 4 and 3/5. Again, we read our answer starting up at the top. 4 and 3/5. We're reading clockwise. And that arrow is going clockwise. That red arrow is going clockwise. The arrow that has the 1 by it. 4 and 3/5. That's our answer. Great job. Dividing fractions. 1/3 divided by 5/9. 1/3 divided by 5/9. We get the reciprocal, or we flip the 5/9 and make it 9/5. Then we ask, is there a number that can go into 1 and 5? What's the highest number that can go into 1 and 5? Nothing. What's the highest number that can go into both 3 and 9? The highest number that can go into both 3 and 9 is 3. 3 going to 3, 1 time. Slash the 3 out and put the 1. 3 goes into 9, 3 times. 1 times 3 is 3. That gives us our numerator answer. 1 times 5 is 5. That gives us our denominator answer. The answer is 3/5. Great job. We go down to the next problem. 5 and 1/2 times 1 and 2/3. We multiply 2 times 5 gives us 10 plus 1 is 11. 11/2 divided by 5/3. How do we get 5/3? We multiplied 3 times 1 gave us 3 plus the 2 gives us 5. Now we have 11/2 times 5/3. Don't forget, in dividing fraction, we have to get the reciprocal of the right hand fraction. Therefore, we have 11/2 times 3/5. We multiply the numerators, we get 11 times 3 is 33, and 2 times 5 is 10. Now we have an answer of 33/10. But remember, we can't have an answer that's an improper fraction. Therefore, we divide the denominator into the numerator. 10 goes into 33 3 times. Therefore, we have an answer of 3 and 3/10. The answer is 3 and 3/10. Great job. Fraction to decimals. Every fraction can be converted to a decimal by dividing. The first problem here is 3/4. 3/4 can be converted to a decimal by dividing 4, which is the denominator, into 3, which is the numerator. 4 goes into 3.00.75 times. So 3/4 can be converted to 0.75. The next problem is 1/4. 4 divided into 1.0 is 0.25. So 1/4 is the same as 0.25 or 25/100. 3/4. 3/4. 4 go into 3.00.75 or 75 hundredths. So 3/4 is the same as 0.75 or 75 hundredths. And if we wanted to convert that even further, we can say 75 hundredths. If we move the decimal place 2 places to the right, if you remember your earlier rules, 2 decimal places to the right will make that 75%. And if we're at 75% and we want to convert it to a decimal, we move the decimal places 2 places back to the left, and we have 0.75 again, or 75 hundredths. Measurements, the English system. These are measurements that are used in everyday math. First is the inch. The abbreviation is IN, period, or the inch symbol. An example might be 7 inches or 7 with the inch symbol. Foot. Foot is abbreviated FT or the foot symbol. An example might be 3 feet or 3 with the foot symbol. Yard. Yard is abbreviated YD, and it can be written as 8 yards. Mile is abbreviated MI. An example might be 23 miles. Now, 1 inch is equal to 1/12 of a foot. 1 foot is equal to 12 inches. 1 foot is also equal to 1/3 of a yard. 1 yard is equal to 36 inches. 1 yard is equal to 3 feet. 1 mile is equal to 5,280 feet. 1 mile is equal to 1,760 yards. Jean Ernest Matzliger. He was a man that used math to revolutionize the shoe industry in the world. He invented the shoe lasting machine. Prior to his invention, there was no machine to connect the uppers of a shoe to the soles of a shoe. This whole process had to be done by hand, which took a very long time. Jean was born in Suriname, or Dutch Guyana, on September 15, 1852. At the age of 10, he was made an apprentice in the government machine shop. There he showed great talent at mechanics. He worked there for a number of years, then moved on. He eventually went on and made this great shoe lasting machine and got a patent for it. He worked very hard at his invention. He had to have math down to come up with such an invention. This goes to show how math and having a desire to create out of your head can take you a long ways. So when you think of shoes, think of Mr. Jean Matzliger for coming up with the shoe lasting machine, which connected the upper parts of the shoe to the soles of the shoe. Here is his machine. Thank you, Mr. Matzliger. Introduction to algebra. The arrows on both ends of the number line show us that the line stretches to infinity. Infinity means there's no end. 0 is neither positive nor negative. An integer is a whole number that can either be less than 0, called negative, or greater than 0, called positive. Negative numbers are indicated by arrows pointing to the left. Positive numbers are indicated by arrows pointing to the right. We don't have to include a positive sign when we write positive numbers. However, we do have to include the negative sign when we write negative numbers. Adding integers on a number line. Every negative integer has a positive integer in equal distance from the origin. -6 integer is an equal distance from 0, the origin, as +6. They're opposites, in other words. 2 integers are the same distance from the origin in opposite directions are called opposites. -3 is the opposite of +3. Absolute value of a number is the number of units that a number is from 0 on the number line. Again, the absolute value of a number is the number of units that a number is from 0 on the number line. Great job. The symbol for absolute value is 2 vertical signs. In this sample, the absolute value of -7 is 7. The absolute value of 7 is 7. More absolute value samples. The absolute value for negative 3 is 3, because the absolute value of a negative number is its opposite. The absolute value for 3 is 3, because the absolute value of a positive number is itself. Adding integers on a number line. The first problem we have is positive 4 plus negative 9. If we go to the right and count 4 from 0, let's count 1, 2, 3, 4. And once we get to the 4, we count back to the left to the negative side 9 places. I'll give you a little time to do that. You should have gotten negative 5. Negative 5 is your answer. The second problem is negative 3 plus positive 5. We're going to go 3 places to the left from 0. 1, 2, 3. And once we get there, we count 5 places back to the right. I'll give you a little time to do that. 1, 2, 3, 4, 5. Look and see what your answer is. Your answer should have been a positive 2. Great job. The next problem. Negative 1 plus negative 4. Let's count from 0 to the left. 1. Then we stop. Once we get to 1, we continue to go to the left and count 4 more places to the left, which is negative 4 places to the left. We're at 1. Now let's count. I'll give you a little time to do that. Your answer should be negative 5. Great job. Adding integers on a number line, the shortcut method. If the signs are the same, add and keep the sign in front of the answer. Again, if the signs are the same, add and keep the sign in front of the answer. If the signs are different, subtract and keep the sign of the highest number in front of your answer. This is a shortcut method to allow you to do the same thing that the number line does. Again, this is a shortcut method that allows you to do the same thing that the number line does. But you'll be able to look at the numbers and basically you'll say, are the numbers the same? And do they have the same sign in front of them? Or are the signs different? And if the signs are the same, you know you add and keep the sign in front of the number. If the signs are different, you automatically know you subtract. Let's look at the first problem. A positive 5 and a negative 9. So the first thing that comes to your mind should be, these signs are different. So I automatically know I subtract. And then I keep the sign that's in front of the highest number, which will give you what? A negative 4. Great job. The next problem. A negative 7 and a positive 13. Those signs are different. So the first thing that should come to your mind is, these signs are different. So I know I have to subtract. And once I subtract, I keep the sign that's in front of the highest number. What is your answer? Your answer is a positive 6. Great job. Positive 6 and a negative 3. Those signs are different. So the first thing you're going to do is subtract. And keep the sign that's in front of the highest number. And your answer is what? A positive 3. Great job. Positive 13 and a negative 7. The signs are different. So the first thing you're going to do is subtract and keep the sign that's in front of the highest number. And that'll give you a negative 4. Great job. Okay, now you have to look at this next problem real close. You have a positive 8, a negative 1, a negative 9, and a positive 6. But that's not a big deal. Get your two negative signs together, which is a negative 1 and a negative 9. Add those two together, and that's going to give you what? A negative 10. Great job. And then you get your two positive signs together. You have a positive 8 and a positive 6. Now, a positive 8 and a positive 6 are going to give you a positive 14. You bring that answer down. Now you have a negative 10 and a positive 14. Now you're right back to the point where the other problems that you did earlier. You have a negative 10 and a positive 14. The signs are different, so the first thing that comes to your mind should be, oh, they're different. So what do? I subtract and keep the sign of the highest number, and your answer is what? A positive 4. Great job. More adding integers. A positive 3 plus a positive 20. Your answer should be positive 23. Positive 6 and a negative 8. Your answer should be a negative 2. A negative 5 plus a negative 3. Your answer should be a negative 8. Negative 12 plus a negative 13. Your answer should be a negative 25. A positive 1 plus a positive 18. Your answer should be a positive 19. A positive 5 plus a negative 7. Your answer should be a negative 2. Great job. Welcome to the world of geometry. A circle contains 360 degrees. A degree is part of a circle. Here is the symbol for a degree. Here is an angle. An angle is formed when two sides meet at a point. The lines that form the angle are called sides of the angle. The point where the lines meet are called the vertex. Angles can be very small or very large. The size of an angle depends on the opening between the sides. A large angle has more opening than a small angle. Turning the angle does not change its size. Changing the length of one or both sides of the angle does not change its size. Types of angles. The first angle is the acute angle. An acute angle measures more than 0 degrees, but less than 90 degrees. Acute angle. Acute angle measures more than 0 degrees, but less than 90 degrees. Right angle. A right angle measures exactly 90 degrees. A right angle is often indicated by placing a small square at its vertex. Right angle. A right angle measures exactly 90 degrees. A right angle is often indicated by placing a small square at its vertex. Lines that meet at a right angle are called perpendicular lines. This is the symbol for a perpendicular line. Lines that meet at right angles are called perpendicular lines. This is the symbol for a perpendicular line. Obtuse angles. An obtuse angle measures more than 90 degrees but less than 180 degrees. Obtuse angles. An obtuse angle measures more than 90 degrees but less than 180 degrees. Straight angles. A straight angle measures exactly 180 degrees. A straight angle is the same as a straight line. Straight angles. A straight angle measures exactly 180 degrees. A straight angle is the same as a straight line. Geometry. A circle contains 360 degrees. Pairs of angles. Complementary angles. Complementary angles are angles whose sum is 90 degrees. Angle QRT and angle TRS are complementary angles. Angle QRT and angle TRS is equal to 90 degrees. Look at this problem closely. Angle TRS is equal to 38 degrees. Now, what is angle QRT? How many degrees is angle QRT? Well, if you look at the problem very closely, you'll see this is a 90-degree angle. Well, if 38 is already given, all you have to do is subtract 38 from 90. Once you do that, what is your answer? Your answer for angle QRT is 52 degrees. Great job. How do we know that's right? 52 plus 38 is equal to 90 degrees, which makes it a complementary angle. Great job. Again, complementary angles are angles whose sum is 90 degrees. How do we know it's right? Because 52 plus 38 is equal to 90 degrees, which makes this angle a complementary angle. Great job. What is your answer for angle ABD? Look at it closely. Now it's a 90-degree angle, and they're giving you 30 degrees. So what do? You subtract 30 from 90, and your answer for angle ABD is what? Your answer for angle ABD is 60 degrees. What is your answer for angle TRS if 40 is already given? Your answer for angle TRS is 50 degrees. What is your answer for angle XYO if 58 degrees is already given? Your answer for angle XYO is 32 degrees. 58 plus 32 is 90 degrees, which makes it what? A complementary angle. Great job. Supplementary angles. Supplementary angles are angles whose sum is 180 degrees. Again, supplementary angles. Supplementary angles are angles whose sum is 180 degrees. In this problem, angle BCR and angle RCD are supplementary angles. Angle BCR and angle RCD is equal to 180 degrees, which makes it a supplementary angle. Now, 50 plus 130 is equal to 180 degrees. This makes it a supplementary angle. Great job. What is angle MNP? Angle MNP is 130 degrees. 130 plus 150 makes what? 180, which makes it what? A supplementary angle. What is angle DBC if 37 degrees is already given? Remember, subtract 37 from what? 180. What is your answer for angle DBC? Your answer for angle DBC is 143 degrees. What is your answer for angle OPT? Your answer for angle OPT is 40 degrees. 140 plus 40 makes 180 degrees, which gives you a supplementary angle. Great job. Squares and square roots. Square of a number is that number multiplied by itself. For example, the square of 3 is 3 times 3 is 9. In symbols, we write the square of a number as a base and an exponent. 3 times 3 is written as 3 squared. The exponent 2 tells how many times the base 3 is written in the product when multiplying. We commonly read this as 3 squared. 3 squared is 9. 7 squared is 49. 9 squared is 81. 6 squared is 36. 2 squared is 4. And 5 squared is 25. Great job. Square roots. The square root of a number is found by asking, what number times itself equals this? For example, what number times itself equals 9? The answer is 3 because 3 times 3 is 9. This is called finding the square root of 9 and can be written as the symbol shown here with the 9 in it. Here is a table of perfect squares from 1 to 15. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. And 15 squared is 225. And what do we mean by squared? We mean that number multiplied times itself. Great job. Garrett A. Morgan. Garrett A. Morgan was born on March 4, 1877 in Paris, Kentucky. Garrett went to elementary school in his hometown but did not have any more formal education. When Garrett was 14, he left home. In today's society, we leave home around 18 or 19. But back during Garrett's time, it was not uncommon to leave home at 13 or 14. He left home and went to Cincinnati. He eventually moved to Cleveland, Ohio. Garrett only had 10 pennies in his pocket when he got to Cleveland, but it did not discourage him. He wanted to be somebody, and he knew he had a brilliant brain. In Cleveland, he taught himself about the sewing machine. He became an expert on the machine and got other jobs. He became so great at repairing sewing machines, he decided to work for himself and open a shop that sold and repaired sewing machines. Think of the math Garrett had to know to get the timing of the needles back in sync, or measuring various fractions as he worked in the shop. Without math, Mr. Morgan could not have been so successful. He eventually earned enough money to buy his own home. Then in 1907, he opened a tailoring shop that manufactured dresses, coats, and suits. he discovered his first invention in his large shop. Mr. Morgan was so successful, he hired 32 workers in his shop. He had a problem that nagged him greatly. The needles on the sewing machine moved so fast that it burned the thread on the wool material by the heat of friction. He eventually discovered a chemical solution that he put on the needles to cut out the scorching and reduce the friction. Garrett, in other words, discovered the first human hair straightener. He went on from there in 1913 and started G.A. Morgan Refining Company and made a lot of money. Mr. Morgan did not stop there. We have to thank him for coming up with the device we call today the gas mask. You see, once your mind opens up mathematically and that light comes in, it just keeps on clicking. Garrett called this device the breathing device. He got a patent in 1914. Just think of all the math he had to know to pull off this great task. Just imagine, he stayed up night and day calculating, figuring, measuring. The whole world is centered around math. To be a creator, an inventor, a carpenter, an engineer, a graphic artist, and many other things, you have to have math down. During World War II, Mr. Morgan's gas mask was improved upon, and it saved many lives as America fought against Germany. Once that light opens up in your mind, nothing can stop you from there. One day, Garrett saw an accident between a horse and a carriage and an automobile. The two hit each other at an intersection. The people in the wreck got hurt very bad. This bothered Mr. Morgan so bad, he did something about it. He did not just sit there and say, "That's a shame." He went back in his shop and did something about it. He came up with the electric traffic light that told people when to stop and when to go. So when you ride down the streets of the world and you stop at a traffic light, thank Mr. Garrett A. Morgan, a thinker, an adventurer, the scholar, the man that always said in his action, "I can do whatever my mind conceives." Here's a man that left home at 14, had only an elementary education, but always believed in himself. And by him having belief in himself, he went on and did the impossible. Thank you, Mr. Garrett A. Morgan.